In this video, we're going to talk about Dalton's law of partial pressures and how it applies to collecting gaseous samples over water. So Dalton's law states that the total pressure of a gaseous mixture is going to be equal to the sum of the partial pressures that result from each of the component gases in the mixture. So a great example of this is in Earth's atmosphere, where you have a total pressure at sea level of 760 millimeters of mercury. So that pressure comes from what you get when you add all of the component gases pressure. So you can see that nitrogen has a pressure of 594, oxygen has a pressure of 158.63, and then you have a little bit of argon, a little bit of carbon dioxide, and then trace amounts of other gases that contribute to that total. So again, the total pressure is going to be equal to the sum of the partial pressures of the component gases in the mixture. Now, when we apply that to collecting gas over water, typically what's going to happen is you have an inverted tube that's filled with water. And then as you add gas to the tube, you're not just going to have that pure gas in the tube. You'll also have some water vapor present. So you can't just say that all of the gas that's in there is from what you're making. There's going to be water vapor in there as well. Now, at the point in time where your water level in the inverted tube is higher than the surrounding water, what you have to account for is that your total pressure is going to be equal to the pressure of water and the pressure of the gas, but you also have the pressure of the liquid water as gravity is pulling it down, and that's applying a pressure as well. So you can't just say that the pressure outside is equal to the pressure of the gases inside. However, when you get to the point where the water level inside the tube is equal to the water level outside the tube, you can say that the pressure outside the tube is equal to the pressure inside the tube. And you can say that the total pressure is equal to the pressure from whatever gas you're making, plus the pressure of water vapor at that given temperature. And as it continues to fill, it'll go past that level sometimes, and then you can't say that the pressures are equal anymore. You would also have some water pressure coming from outside the tube pushing in, and you would have to account for that. So if you're measuring the volume of the gas that you're generating, you want the water levels inside and outside of the tube to be equal. And it should look like that. And you can see that you can rearrange Dalton's law to solve for the pressure of the gas inside, what we would call the dry gas pressure, by simply subtracting the pressure of water vapor from the atmospheric pressure to get the value of the pressure for your gaseous sample. Now, the pressure of water vapor is completely dependent on temperature. The higher the temperature, the more water vapor is formed, and the higher pressure you'll get that results from the water vapor. And you can see that it increases here, and it gets really high. And notice that when it gets to at a temperature of 100 degrees, which we know is water's boiling point, that it has a pressure of 101.32 kilopascals, and that's atmospheric pressure. Applying this to a gas problem, here we go. Hydrogen gas is generated in a total volume of 35 mils of gas is collected over water. The temperature of the experiment is 22 degrees, and the pressure is 755 millimeters of mercury. That's the atmospheric pressure at that point in time. Solve for the pressure of the dry gas. So at 22 degrees Celsius, water would have a vapor pressure of 19.8 millimeters of mercury. So what we can do is rearrange the equation like we showed on the previous slide and just solve for that pressure of the hydrogen gas. So it's 755 millimeters of mercury as the atmospheric pressure, or total pressure, minus the 19.8 millimeters of mercury from the water vapor, and that would leave you with 735 millimeters of mercury of pressure from the dry gas. So that was Dalton's law and how it applies to gases collected over water.